So I might start. Thank you, everyone. We are having our first session, like contributed session, and the topic's advanced data and analytics. And we have 4 talks today, and they are 10 minutes talks. I might let you know when you have a couple of minutes to go. I could go 5 in a couple of minutes. Depending on how the pace goes. But we have the 4 talks, and then we have Q&A, 5 minutes Q&A in the end of the talks. So if you have questions, please post them on Slack, and I will read them in the end. And if we don't have time to address all the questions, the speakers will reply to them on Slack. So it would be really good if you could type your questions there so they can follow up with that afterwards. So without any more delay, I will introduce our first speaker. So he is speaking from Perth. It's Eben Afrifa Yaumoa. Please correct me if I'm pronouncing anything incorrectly, your name. Great, thank you. And he's talking about conceptualized psychomedical footprint for health status outcomes and the potential impacts of early detection and prevention of chronic diseases in the context of 3P medicine. Thank you so much, Evan.
All right, thank you for the introduction. So I'm with Edith Cowan University, a lecturer in statistics. So we know psychometrics has served the behavioral science and then social science quite well in terms of gathering data and then based on perception, being able to make very informed inference about concepts that they may be interested in. So in a medical setting, it's not quite common to see the use of psychometrics, but we are pushing to get psychomedical instruments being used for disease diagnosis, especially in the context of 3P. So chronic disease, as we all know, we call them lifestyle diseases. And then the prevalence and then the burden of chronic disease is quite enormous. So the map here is the distribution of people who are living with a disability because of a chronic condition. So this was updated in 2023. So you could see that nowhere is safe. We are all at risk when it comes to these chronic conditions. So the motivating questions for this work and then the line of work I do in this area is, did you know that chronic diseases send warning signals up to 30 years before diagnosis? So what if subjective symptoms are the earliest predictors of metabolic diseases? And how might healthcare transform if we validate patients' experiences as much as we do with lab results? So this is the status quo, where when we want to diagnose, you go and then maybe you take a pint of blood or some fluid, and then it has to go through several processes, instrumentation, analytics. And when I go back and then you look at the most endemic area in the world, you can see that it's Africa, and then Asia is also there. So these countries are mostly less developed, where they might not have access to instrumentations and then all those sophisticated machines that are required in the phase of diagnosis. So these objective markers, as we've believed in them, they become abnormal when the disease has progressed to an advanced stage. And when we overly relied on these objective markers, we can overlook important clinical symptoms that can help us. And then they are very expensive, which require instrumentations. So can we use patient-reported symptoms and the functional changes that may precede these measurable changes to predict diseases. So this is where we want to shift away from reactive to preventive and then predictive personalized medicine. So can we rely on subjective markers instead of objective markers in managing the burden of chronic diseases? And this is where our research fits in, where we've developed this psychometric instrument, which is the 25 item questions that is looking at suboptimal, predicting your suboptimal, predicting your optimal health status. So whether you are in an optimal state or you are in a suboptimal state. So what this tool is helping us to do is to define you as optimal and then to define you as suboptimal, because we know that when you are in the suboptimal phase, that is where you make all those ambiguous complaints about your health. You talk about several things ranging from fatigue, headache, and then all those complaints, which sometimes clinical practitioners overlook them in terms of predicting conditions as severe as chronic conditions, say diabetes or any cardiovascular condition. So we are looking at our health in 5 dimensions, where we are asking questions on your fatigue, your mental state, your cardiovascular system, immune system, and then your respiratory or digestive system. So we have these 25 items that are helping us to measure your health status. And then the instrument has been validated in China, it has been validated in Russia, Ghana, and then Korea. So this is the 25 item questionnaire. And if you look at the figure on mine right, you could see that we've tried to identify the various chronic conditions that you could observe when you follow any of the dimensions. So if you follow a person in the continuum, these are the conditions, the chronic conditions they could develop, being it, looking at it from the digestive system, mental health, and then the others. So can we use this as an innovative screening tool that can help us identify people who are really at risk and then help mitigate the conditions, because we call them lifestyle conditions. And then if we are able to predict them early, we can reverse the onset of those conditions. So in this work, which has been published in EPMA journal, which is a leading journal in preventive, predictive, and personalized medicine, we are looking at how we could bring in data visualization, be able to visualize these 25 items and then the 5 dimensions to help in the prediction and then to support personalized medicine. So here, as a screening tool, we screen our general population, ask them questions, and then the questions, as you saw, are very straightforward. Just tell us how you feel. So it's a 5 scale questionnaire where it's never often, very often, or always experiencing those sort of conditions. So we are trying to explore the internal structure of these 25 items, and then if indeed it has that discriminatory power to predict optimal and then suboptimal status. So with this, then we can bring in the visualization where we can produce the photogenic representation of the distinct relationship pattern for our instrument in terms of measuring the health status of an individual. So in this work, we did a network analysis where we applied the graphical lasso model. And then for us to be able to compare the graphical orientation, we use the multi-dimensional scaling configuration to be able to compare the network that will be constructed for the 2 groups. So that is the study design. where we apply the questionnaire. And then at this stage, we are using a medium cutoff to distinguish the optimal and then the suboptimal. So if you are below the median cutoff, you are in the ideal or the optimal state. If you are above, you are in the suboptimal state. So this stage is where we see that you are in the process of developing a condition.
Just
so
a couple of minutes.
Briefly, this is the statistical modeling framework. So we are trying to, because we are using lasso, it's a penalized log likelihood that we are trying to maximize. And it uses the theory that was proposed by Friedman and colleagues in 2008 on the graphical lasso model. So here are some outputs in terms of results. So you can see that for the optimal and then the suboptimal state, the graphical configuration is quite different. And that do suggest that the two has that discriminatory power. And then at the dimensional level, you can see that there is also difference in the configuration. But moving on is the most important thing for us in terms of how we could use that instrument in longitudinal studies, and then also how we could bring in machine learning. So I was really happy when the keynote speaker talked about synthetic data, because that is where we are moving to synthetic machine learning, to be able to generate several data sets to train models to predict these two groups. And we know that because of the population dynamics, we will have to segment with age, look at different age groups so that we can come up with thresholds for each of the age groups. And we believe with this, we'll be able to improve prediction, and then we'll be able to prevent these conditions, which will save the healthcare a lot. Thank you for your time.
Thank you so much, Evan, for the great talk, and it's a great topic as well, very important case study. And now we are moving on to our second talk. Please don't forget to add your questions to Slack. So we'll go to that in the end. So our second talk is by Takeshi Tauja Damarachne. So it's on saturated design-based statistical methods for variable selection in observational data, mixed case data case. So thank you so much, Karkesh. If you could please share your screen.
Sure.
Thank you so much. And we have 10 minutes. I'll let you know when you're a couple of minutes to go. But if you want any earlier sign, just let me know.
Can I see the screen?
Yes, perfect.
Sure. Hello, everyone. Today, I'll talk about supersaturated design-based statistical methods for variable selection in observational data, particularly using mixed data, which consists of both a numeric and binary form of data. Firstly, if I talk about data, with the advancement of technology, ample of data are gathered and are available to be analyzed in all the fields. These data can mainly be classified into two groups based on the way they are collected, particularly either following an experimental or an observational study. Based on the sample size and the number of input factors, this data can be further classified. For instance, if the sample size is less than the number of input factors, in experimental studies, such designs are known as supersaturated designs, while in observational studies, such data are known as high-dimensional data. Following data collection, one primary objective is to assess the association between the outcome and the input factors. A common approach for this purpose is to fit a regression model, where in my case, I will consider multiple linear regression model. However, a key challenge in current studies is that data collected on a large number of input factors, but only few of these many input factors tend to have a significant influence on the outcome, which I call them as significant factors. Currently, model building also tends to model building also tends to perform only including these significant factors. Therefore, it is vital to select these significant factors accurately. Several variable selection methods, including classical and modern variable selection methods, are therefore introduced to identify these significant factors. But none of these methods have been proven to be performing exceptionally well over the other methods. But interestingly, some of these methods have been modified and applied on supersaturated designs for factor screening purpose. However, it has not been tested in other way around, particularly using contrast-based statistical methods, which motivated me to try and attempt to apply a contrast-based supersaturated design-based statistical method on observational data to identify these significant factors. Therefore, in this study, I will investigate how well the proposed contrast-based supersaturated design-based statistical method will select the significant factors compared with the existing statistical methods in the literature using simulated mixed data. After reviewing literature, I selected a contrast-based supersaturated design-based statistical method known as singular value decomposition principal regression method. This method is initially introduced to identify significant factors from a data set where all the input factors are of binary form and the outcome is numeric. Therefore, I modified this method accordingly so that it can be applied on observational data, which includes both binary and numeric data. I then wrote an R code for this modified method and call it as SSD-SVD method. This method selects important factors following 7 steps. Firstly, which includes computation of standardized contrast, performance of singular value decomposition, linear regression model, and lastly, conducting hypothesis test in order to assess the significance of the regression coefficient estimates based on which the important factors are selected. Then for the comparative study, I selected 10 existing variable selection methods, including both classical and modern methods. Then I designed the simulation study initially by generating the model matrix, similarly to Wallis 2021 study with 17 input factors, including both numeric and binary factors with random correlation. I simulated data sets with 4 different sample sizes in order to assess the variable selection performance with different events per variable measures. The CPV measure is calculated by dividing the sample size from the total input factors. Also, the significance level was set to be 0.05. Furthermore, in this simulation study, 8 of the 17 input factors were set to be truly significant, denoting them to be true predictors. Therefore, non-zero coefficient values were assigned for the first 8 of the 17 input factors, while the coefficient of the false predictors was set to be 0. Once simulating a dataset with a specific sample size, the response vector was computed using equation 3. Then each candidate method was applied on this simulated dataset and stored the input factors, which got selected as potentially significant. Finally, this process was repeated 1,000 times. Following simulation study, the variable selection performance was evaluated using several summary measures. Firstly, by computing type 1 and type 2 error rates. Then I also computed the number of simulations which selected just the set of true predictors as the output and recorded as a percentage using true model selection frequency. I also computed the percentage variable inclusion frequency in order to assess the likeliness of each input factor getting selected as significant under each method.
Just a
Next,
couple of
let's look
minutes.
at the results section obtained following the simulation study. If we firstly look at the overall summary statistics, according to type 1 error rate on to the left, the SSD-SVD method in red and backward elimination BIC method in light green both performed well in avoiding the false predictors from getting selected to the model across all the sample sizes by recording a type 1 error rate closer to 0. According to type 2 error rate in the middle, the lasso with lambda minimum minimum penalty in black color perform best in identifying the true predictors across all the sample sizes. While none of these methods perform best with respect to both the error rates, according to true model selection frequency figure on to the right, the backward elimination BIC method performed best, particularly with the sample size of 425. In this slide, I have provided the variable inclusion frequency measures produced for each input factor under each method. The true predictors are presented in red color, while the false predictors are presented in blue, and they are separated by the vertical line superimposed on each figure. By referring this figure, this summary measure, lasso with lambda minimum penalty, both adaptive lasso, elasticness, and both group lasso methods cannot be recommended for variable selection, as these methods either recorded larger variable inclusion frequency measures for false predictors or struggle to identify at least one true predictor. Among the remaining 5 methods, backward elimination AIC and backward elimination 0.05 performed equally well in identifying the true predictors by recording a VIF of at least 50% for all the true predictors across all the sample sizes. But both these methods tend to include false predictors as well. Therefore, with respect to false predictors, backward elimination BIC and the SSD-SVD method perform best in recording lowest VIF methods values for all the false predictors across all the sample sizes. In addition to recording lowest VIF measures for false predictors, backward elimination BIC also recorded VIF measures beyond 50% for all the true predictors when the EPV value of the data set was equal to 50. By referring all the summary measures, we strongly recommend to use the VIF measures to assess and compare the variable selection performance of the candidate methods. Thereby, we recommend to apply backward elimination BIC method on data sets with an EPV of at least 50% to identify the significant factors. For the case where the EPV of a data set is less than 50, we recommend to assess the significance of an input factor by referring the VIF measures computed by backward elimination AIC and the SSD-SVD method. Last but not least, the SSD-SVD method performed well compared to several modern variable selection methods, showing the potential use of the supersaturated design-based statistical techniques in observational studies for variable selection. Before winding up, I have provided few references, and with that, I would like to conclude my presentation. Thank you.
Thank you so much, Kanish, for a very interesting talk and a very interesting study as well. So next, we have some results relating the construction of frequency squares from cellular automata, and it's going to be presented by Vindhya Nikshadi Warnakula Suryaji. Hopefully I pronounced correctly. So, and is joining us online. Who's joining us online? So Vindhya, you can see your slides.
Okay. Can you hear me now?
Yes, we can hear you well. Thank you so much.
All right, no worries. Hi everyone, I'm Vindhya Varnakula a PhD student from RMIT University, Melbourne. Today my topic is some results relating the construction of frequency square from cellular automata. And I would like to take this opportunity to thank ECSSC for giving me this opportunity to present as well as the funding. Oops. Before starting the presentation, I would like to acknowledge the country. I acknowledge the people of the Woiwurrung and Bumurrung language groups of the Eastern Kulin Nation, on whose unceded lands we conduct the business of the university. I respectfully acknowledge their ancestors and elders, past and present. I also acknowledge the traditional custodian and their ancestors of the waters across Australia, where we conduct our business. To begin, imagine we need to test 3 different treatments for COVID, each with 4 possible doses. Normally, we would conduct 64 tests to cover all possible combinations. But what if I told you we could reduce this number to just 16 tests? Interesting, right? So The concept, the mathematical concept or the combinatorial object to tackle that problem is mutually orthogonal Latin squares. What is this mutually orthogonal Latin square? A Latin square is an n by n array having n different symbols such that each symbol appears exactly once in each row and each column, like this. Two Latin squares are said to be orthogonal. If we superimpose first one with the second one, we get all distinct ordered pair. Moving on to the set of Latin square, which are pairwise orthogonal, we refer to be mutually orthogonal Latin squares. Moving back to the problem, the initial problem, where we optimizing the experimental design, each Latin square, if we represent each Latin square with the treatment of the COVID and each symbol within represent a different dose, if we combine them all together, then we can just conduct 16 tests instead of 64. That's how these mutually orthogonal Latin squares are important. Right. The Latin square can be generalized in several ways. One such way is called frequency square. And the Latin square, each symbol, the frequency of each symbol is 1, while when we come to the frequency square, each symbol have the same frequency. For example, L is a Latin square. If we transform 4, 5, 6 in L with 1, 2, and 3 respectively, we can have S, where we only have symbols to be 1, 2, 3, and each symbol have the frequency 2 in each row and each column. And this frequency square type is 6 semicolon 2. Here 6 is the order and 2 is the frequency of each element. When the frequency is 1, then the frequency square is a Latin square, and when the frequency is equals to the order, then the frequency square is called trivial square. In my research, I'm using the concept called cellular automata to construct frequency squares. To explain the concept of cellular automata, think of tracking COVID-19 spread. We monitor 5 people, each either following social distancing rules or not based on a simple guideline. This guideline states that a person will strictly follow rules if only one of their neighbors does so. Starting with only one person strictly following the rule, we can determine the behavior of others over time. This process helps us understand how interaction affects on the behavior, and which similar to the cellular automata concept. The formal definition for the one-dimensional cellular automata is given in this slide. We have finite alphabet A with Q element, a cellular automaton, the plural version is cellular automata. Curly F can be determined with respect to the local rule simple F with the diameter D as this way. And here we consider the finite alphabet A to be F2, and the local rule can be represented by the Wolfram code. All right, the next thing is the square associated with cellular automaton. We can always get a square from a cellular automaton, whether it is a frequency square, Latin square, etc., etc. But the formal definition is if the cellular automata is order 2 times d minus 1, then we can get a square of order q to the power d minus 1. Since we are dealing with the finite alphabet A to be F2, we always get a square of order 2 to the power d minus 1. And this table shows us the computational results we got from the frequency square generated from cellular automata up to the diameter less than or equal to 5. For example, when the diameter 2, we got 4 frequency squares of order 2 with respect to the local rule 0, 6, 9, 15. These are the Wolfram code of the local rules. When it's come to the diameter 5, we got 258 frequency squares of order 16. And the observation we found throughout this, the computational results is that we always get these frequency squares either Latin squares or trivial squares. Not only that, but also we found that the total number of frequency squares generated from the cellular automata per particular diameter d, which is less than 5, equals to 2 plus the total number of Latin squares generated from cellular automata. Here this 2 is the number of trivial squares. Based on these computational results, we established some conjectures for the Latin squares as well as the frequency square, which is trivial frequency squares. And we proved, and we based on that we established some lemmas and theorems. And here I have given the sufficient condition to generate trivial squares, or it is a frequency square of the type 2D minus 1, 2D minus 1. Here it says that if the local rule is a constant function, then the square associated to the cellular automata is a trivial square. And this theorem, it says that the necessary condition to generate trivial square from a cellular automata, which is also the necessary condition too here, and which is the local rule should be a constant function. If I just give you some hints on the proof of this theorem, what we did here was we assume that this the local rule function is not a constant function, and we were trying to prove that the resultant square is not a trivial square. So that what we have to do is choose two entries of the square, and we were trying to prove that these two entries are not equal. And we used the principle of mathematical induction to prove this one. And the base case was the D equal 2 case, and we proved that using the computational results. And the inductive assumption is when D is less than or equal to R, this constant, the B constant function is the necessary condition, and we try to prove that using that inductive assumption when D equal R plus 1, and this fx not equal to A. And that's how we prove the theorem. To conclude, we try to prove that we try to construct frequency square, which is a generalization of Latin square, which plays an important role in the statistical combinatorial design theory. And we use the concept called cellular automata with diameter D with finite set F2, and we have the corresponding square of order 2 to the power D minus 1. We found that being a constant function is the necessary and sufficient condition to generate trivial square from the cellular automata. As a future works, we are trying to extend these works to explore the other type of frequency squares, which means other than Latin squares and trivial squares, and to determine the condition for generating mutually orthogonal frequency square. And that concludes my presentation. These are my references, and thank you very much.
Thank you so much, India, for such an interesting presentation. And now we have Solomon Wonder Johannes presenting from Hobart on model choices and variable estimation methods for assessing healthcare providers' performance in treating ESKD patients close to home. Thank you so much, Solomon, and I'll let you know in a couple of minutes.
Thank you very much for introduction. Hi, everyone. I'm Solomon Johannes, a research fellow at Monash University, working with Professor Paul Lawton, senior NHMRC research fellow, and Yome Jones, who is the manager of the Return to Country project, which I'm going to discuss in a bit. So today I'm gonna present the methodological development behind this project and the challenges we faced in using various models and variance estimation approaches for interpretation and comparison of institutions, hospitals, centers in providing health services to kidney replacement therapy patients close to home. So as to my presentation, I will briefly acknowledge country and discuss the background behind the development of this project, which is Return to Country, which is a home-based renal replacement therapy for patients. The then briefly discuss methodology, results, conclusion, and references. First of all, I will start by acknowledging country. We acknowledge the Wuina people, the traditional owners of the land upon which we gather here today. We also pay our respect to the First Nations people who join us here today. So return to country is defined as when a patient receives treatment in the same postcode as the original postcode at treatment start. Currently, under the Return to Country project, we are seeking to assess centers or hospitals' performance in treating end-stage kidney disease patients close to home. So the main objective is to compare between and within a center's performance in providing treatment close to home by comparing the First Nation people versus non-indigenous patients. So the source of the data is ANZ Data Registry, which is a registry which documents kidney patient data. So it consists of individual level patient clustered to treatment centers, hospitals from 2005 to 2003, actually. We have updated that data. And we used a funnel plot approach for comparing institutions in terms of sending patients close to home following transplant or dialysis at a given center 1 year after. So this funnel plot is a graphical approach like Schwartz control chart for controlling quality. So we used that concept to compare institutions, whether they are performing well, if they perform above the false discovery rate. Don't worry, I'm gonna use this as a pointer. So this is the upper false discovery rates, and this is a lower false discovery rate. So any center, hospital, which lies above the false discovery rate is considered to be high performing in terms of responding to the outcome. And those which lies below will be considered as low performing ones. And any center in between the false discovery rate is considered to be an average performing center. So using this background, what is the challenge behind this methodology? Estimation of the variability around the log standardized incidence ratio is a key challenge. And even when we use different models, well, the interpretation and the result really changes. And that affects the interpretation and the conclusion behind this research. So we have on the vertical axis, the log standardized incidence ratio. And on the horizontal axis, we have the effective sum size, which is a reporting technique followed by the ANZ Data Registry for anonymizing centers, de-identifying centers, I think, which is a challenge nowadays in reporting our research finding, which is stressed by our keynote speaker earlier. So we used this data version 18.5 for data management, and for modeling, we used R. So our performance measure is standardized incidence ratio, which is the ratio of observed number of patients receiving treatment close to home to the predicted number of patients receiving treatment close to home. And the predicted number of patients receiving treatment close to home comes from a model prediction. So we used 3 models for that purpose, the logistic regression, binomial regression, and Poisson regression. And these are the calculation behind getting the expected counts for each of the models. And we are in the random effects, logistic regression, Poisson regression, and binomial regression context to get those expected counts. So the method we used is the delta method, which is a first order Taylor-Serre Taylor series approximation. This has been the methodology behind the measure for variance for many years now. But it comes with analytical challenge. And most of the researchers used bootstrapping approach for estimating this variance. As you can see, it comes with lots of challenges because it is, first, it is a binary outcome. We have to get the variance for binary outcome and then for the expected, and then the covariance becomes more and more complex as we go down the derivation of the formula.
Couple of minutes.
So basically, we compared the bootstrap Bayesian approach and the actual delta method analytically to see how that affects the variability and the interpretation of the results. So this is the formula we used for getting the variance estimation from bootstrap, and then this one is the information we used for getting the result from the Bayesian approach. So I'll be rushing. So this is the result. As you can see, the logistic, Poisson, and binomial model, they give us different stories when we fit the three models. So based on the logistic random effects model, the result becomes more or less, the centers, they become more or less within the false discovery rates. Whereas when we use the Poisson model, you can see there is high variability, and most of the red centers, which are indigenous centers, they lie below the lower performance region, and some non-indigenous centers perform above the false discovery rate. And when we use the binomial regression, you can see how the interpretation really changes. So we choose actually the logistic regression for the reason that we can avoid the ecological fallacy due to aggregation in Poisson and binomial regression. So we continued with comparing the delta method with the Bayesian and the bootstrap method. And finally, we got the somehow, reasonable result from the Bayesian and the delta method. And we compared the models using bias, variance, and mean square error for accuracy and consistency of using these methods. And we found out, the MC approach to be the best method for this kind of method or modeling. So this is the conclusion. Model choice is critical and heavily affects the interpretation of the performance of health service providers. And finally, logistic via MC approach turns out to be a good choice. This is a source of the fund. We are thankful for the NHMRC of Australia for funding us, and ethics has been obtained from those institutions listed below. These are the references. Thank you very much.
Thank you so much, Solomon. Such a great work. We have a couple of questions on Slack. We have 1 minute to go. And we just have yet for Eben. I might ask one question if he's quick to answer. Otherwise, if we go over time, then everyone can answer on Slack. So there's a question. So thank you for your talk. I'm interested to know how you are working with clinicians to ensure such a tool is acceptable to them when they may struggle to understand the underlying statistical theory.
Yeah, thank you very much. So the tool was developed in a medical school, and we do have consortiums around where we are trying to link the subjective to objective markers So we need to establish that there is a strong link first. So now we are doing more the background and then the computational side of things to establish that there is consistency in the results that we are getting from the subjective markers and then the objective markers. And I guess with the consortiums, yeah, we'll do a lot of, there will be the need for a lot of discussions where we will hold workshops and then reach out to clinicians in terms of that bit. So there is a whole journal, like I said, the EPMA journal, which is dedicated for predictive, preventive, personalized medicine. So there is a group that is pushing that agenda, and with time, I believe clinicians will come to accept that subjective markers will be a good way in diagnosing these chronic conditions.
Thank you so much, Evan. We are over time now, so I thank you all the speakers from this session for the great talk, and I ask you if you have questions, please type them on Slack and the speakers will try to get to them later. Thank you so much. Continue enjoying your day.
Okay, so we're going to head straight into the next session, which I'll be chairing. So our first speaker is Sam Moffat. Let me get the slides working. Oh, you want to do PowerPoint? Yeah. So just like in the last session, each speaker has 10 minutes. And I will wave my arms when you have 1 minute to go.
Cool. We'll get started then. Thanks everyone for coming. So my talk is identifying team playing styles across phases of play. What we're trying to do is apply some machine learning and data science techniques to Australian rules football. You can change the slides. There we go. So what we want to do is there's a lot of analysis that gets done within football itself at the moment, but that's done by coaches and sports scientists using their subjective knowledge that they've built up over a period of time in the game. And we want to try and simplify that and objectify that analysis. So what we're trying to do is describe how a team plays. So coaches, media, anyone that watches a game might be able to pick up what a team does by actually watching it. So we're trying to use the data that's collected within a match to describe how a team moves the ball, whether it's through kicking the ball, running the ball, handballing the ball, how they actually gain possession of the ball, whether they try and mark the ball off the opposition or they try and gather it through contests and off the floor. And then the final piece is how they defend and how they pressure the ball carrier, how they tackle, and what defensive strategies they're implementing within the game. So what we're trying to do is we think of all the bubbles on the left as the performances that teams have within a game. Is we want to apply a cluster framework to that so that we can then have distinct groups of performance that succinctly describes what a team's done, and the coaches can pick that up without watching a game and go, this is how the team has played. Can we dig deeper and ask more questions after that? So at the moment, a lot of the analysis is done on the whole match level. We want to make this more applicable for in-game analysis and make it more specific to the coach's needs and actually break it down. So we can go to quarter level, but we can even break it down even further into possession chains. So you can see here, there's actually lots of different periods within a game that a coach and the team can change how they can perform. And it's not necessarily going to be consistent across the whole game. So we want to actually break down the data onto this finer scale to give this minute period in a game, this is how a team has performed. So how we want to do this is actually through the cluster framework itself. And there's no one cluster solution for every single data set or every single clustering problem. So what we've actually designed is a framework in itself that can be applied to essentially any clustering solution or clustering problem, and then you get an application-specific clustering solution. So it's made up of the clustering algorithm. We don't know specifically what algorithm is best for our data, so we want to apply multiple methods to the data to then identify which algorithm is the best. The number of clusters, we could say there's only 3 ways that the team perform, but we want to actually use the data to define this and go, there might be 6 ways or 5 ways in the data set and groups. So that's what's going to inform that. And then the third part is your feature standardization. So you want to actually transform the data so that the coaches can interpret it, but also how can we get groups of data within the 3 seasons, 4 seasons that can actually identify through the clustering algorithm and number of clusters. But how do we actually identify the optimal amount? And that's through a composite clustering index. So a lot of standard methods at the moment might use an AWS or ASW score or other standard popular assessment metrics, but we actually want to assess the individual components of the clusters. So whether you want to look at how well the cluster centroid represents the encapsulating data, whether the cluster itself is homogeneous or it has well separated clusters. So there's actually individual metrics that assess this. And what we can do is talk to subject matter experts and figure out what they actually want. Do they want their clusters to be well separated? Would they prefer their clusters to be homogeneous and encapsulate everything within that? So what we actually do then, instead of just giving it a standard weighting for every cluster application that you have, we use the analytical hierarchical process, which actually weights the indexes based on your preference. So if homogeneity is 2 times more important than separation, then it gives a relative weighting score to that to then give a cluster specific solution. So we specifically applied this within the AFL. We got our data through Champion Data, which is their official match provider. We used all of the coding through R, and then we defined that there's going to be a range of playing styles that teams can perform. So between 2 and 10, we don't know what the optimal amount is, but that's what we think is going to be an interpretable amount for the teams. We then apply the clustering algorithms, and then we had our weighted score. So for this clustering problem, we wanted to have our clusters well represented by the clustering, the cluster centroid, as well as well homogeneous clusters. But we also wanted to include the other aspects of cluster density and cluster separation. So they're included in the metric, but they're lower weighted to that. And what this happened, this identified that there was 5 clusters that was the optimal way that teams could play using the K-medioids method. So we use that on the data, and then that gives us our 5 offensive playing styles that teams can do when they move the ball. We're just going to dig deeper into one here. So you can see how a team gathers the ball. They actually gather it through an uncontested possession more than a contested possession here. And then they actually mark the ball. And then when they distribute the ball, it's through a short kick that's effective to teammates. So that's kind of the characterization of any team that gets put into that cluster. Now that we have these clusters and we know how teams play, the coaches might ask more questions to analyze their performance. They might want to know how often teams actually play these playing styles. So different teams across the competition actually perform the playing styles a different amount within a game. So you can see here there's a bias towards specific styles, but not every team has the same amount across the whole year. Now we're looking at the whole year. They might actually want to look at across the one season. Does one team play a different way in different games? So we can actually use the information that we've already identified to summarize that, teams actually play different ways across the season. This might be because they're versing easy opponents. They might be versing harder opponents. It might be wet. It might be dry. But we now know that we can identify that their performance does change across the season. We'll lead again to another deeper question of does the performance actually fluctuate across a match? So current literature analyzes performance at the whole match level. What we've been able to do is actually identify it across a match. And you can see here within the possession chains of the game, teams are actually performing different playing styles at different points in the game. So that might be, has the team changed the way they want to play? Has the opposition forced them to play in another way? So by identifying at the small possession chain level, we can actually then ask the questions of, does this correlate to success? Is it because we're not performing to the way we want to be? Is it because the players we selected aren't doing what they need to do? You might want to, look at the interaction between playing styles and go, do we need to play a specific way when we defend so that we can perform when we have the ball in a specific way? We might want to look at what the opposition does and see that the opposition plays one way, do we play another way to optimize our performance within the game? We might want to look at, coaches might look at the experience of their team versus an inexperience of the team. So do younger players help perform a specific way? Do you need older players? They might not be as good as the younger players, but you need their expertise and experience to help instruct the players on the field to perform a specific way. That one. And then match context. So are we losing? Are we winning? Does that change the way that the team needs to play? So by identifying these playing styles at this level, we can then ask these questions in further research and further analysis of performance. Specifically, we applied this clustering framework to Australian rules football, but you can apply it to any sports. You can apply it to almost any clustering application itself. It's about the framework getting adjusted to that specific problem. So do you need to weight your indexes in a different way to produce different clustering solutions? Or you could even apply different clustering methods themselves if you want to put them in there. Or you can change the number of clusters that you want to identify, not just 2 to 10. You could change that input itself and look at the hundreds of ways that teams play as well. And that's my presentation. Thanks.
Thank you very much, Sam. So our next speaker actually is Dong. Oh, you are here. Sorry. Okay. You didn't grab your badge, so I didn't know you were here. That's right. So we do have our speaker. So I've got your, let me get your slides going. Is that all right? If I do it that way, is that okay?
Hello.
Yeah, go ahead.
Good morning, everyone. My name is Dong, and I'm a PhD student in statistics at the University of Melbourne. And today I'm going to talk about my research in a semi-supervised estimator of the marginal means. So here is the background of the setting of our work. In a typical semi-supervised inference setting, we assume that we have n IID samples of x and y's from the joint distribution of x, y, and also we have a additional unlabeled data set where we have m samples of X from the marginal distribution of X. So it's equivalently, we can think of this as a missing completely at random of the response of Y. So the distribution of X is set the same in both the labeled data and the unlabeled data. And now the problem we're interested in that how are we going to utilize this unlabeled data to improve our estimation of the marginal mean. So John Brown and Tai, they proposed using a linear regression as a working model. So they first fit a linear regression model and get a beta hat with ordinary least squares on the label data set. And then here mu hat is the sample mean of X from both data set. So it's equivalent to saying, okay, we fit a linear regression and then we average the predicted response across the entire data set. So so we are curious that if we can use other working models other than the linear regression as approximation to the conditional expectation of Y given X. So their estimator are consistent and asymptotically normal and has improved asymptotic efficiency compared to the supervised one. So we want to extend it to the case, say, when Y is binary. So in this case, it's natural to consider a like a binary logistic regression to approximate the relationship between Y and X. So an intuitive analog of their method is say, okay, we fit a logistic regression on the label data set, and then we average this fitted response across the entire data set, which gives us this theta hat. But the interesting question is, how do we estimate this beta hat? So if we do this with the maximum likelihood estimator and then plug it in, we do get a consistent estimator and which is asymptotically normal, even if the model is misspecified. However, we notice that this asymptotic efficiency of theta hat is determined by the limit of beta that the beta hat converges to. And we find that the limit of the maximum likelihood estimator, which we denote as beta star ML, is not the optimal beta star when the binary regression is misspecified, in the sense that it does not minimize the asymptotic variance. So we propose the alternative way of we propose the alternative this beta hat constructed as follows. So we have two equations here. The first equation is to ensure that this beta star gives us a consistent estimator. And the second one is that we want to minimize the variance. So now we are constructing a beta hat that converges to the beta star that satisfies these two conditions. So to do that, we just need to consider the empirical version of that constrained optimization problem presented in the previous slides. We denoted that beta as beta hat CLS, which refers to constrained least squares, and then plug it into the previous equation, which gives us theta hat CLS. And we can derive that consistency and asymptotic normality. As for this variance term in the normal distribution, we notice that this is a weighted average between the variance Y and tau squared min. The variance of Y correspond to the variance if we use the sample mean estimator, then the variance component of that normal distribution would be the variance y. So in the case where rho equals 0, that is the case that m, the unlabeled data, is infinite, which is equivalent to mean that we know the marginal distribution of x. The variance component becomes the tau square mean, which is always smaller than or equal to the variance of y by the construction of beta star. So unless y has no correlation to any of the covariate x, and this tau square mean is also then smaller than the tau square maximum likelihood, which means that now we are getting the optimal asymptotic efficiency. So here are some of the simulation results. On the x-axis is the size of the unlabeled data, and on the y-axis is the scaled mean squared error. So the blue dashed line refers to the MSE of y bar, the sample mean. It's constant because the label data size of the label data doesn't change. It's always 500 here. And we notice that there is a drastic decrease of the dashed black line, which refers to the MSE of the semi-supervised estimator. This means that even if we only have a small relatively small size of the unlabeled data, we can still gain a significant increase in efficiency. But as the size of the unlabeled data increases, we have less and less marginal gains. This is because there is always a proportion of the variance y which cannot be explained by x. The results are similar when the model is misspecified. And in the unlikely case where none of the x is correlated with y, we only have a small sacrifice. Okay, sure. So even if, in theory, there's no sacrifice because when n goes to infinity, but in finite samples, we have a small sacrifice, but that's usually a we're willing to make. Yeah, so I think that concludes my presentation today. Thank you.
Okay, thank you very much. Sorry for the IT issue earlier. So we have one more speaker for this session who is joining us from Christchurch, I believe. So Meredith Norman will be speaking on navigating stringent model assumptions through time domain restriction. I hope someone over there will do your time check for you.
Yeah, they will. Cool. Thank you for the introduction. So hello, everyone. My name is Meredith, and I'm a statistician at the Australian Bureau of Statistics. And I just wanted to thank everyone for tuning into my talk, both across Australia, New Zealand, and online. So today I'm going to be talking about a proposed method for navigating stringent model assumptions through time domain restriction. So since some of the conference attendees are still in university and some of us are in industry, I thought I would start my talk by talking about a key statistical difference I noticed between my university studies and my work as a statistician at the Australian Bureau of Statistics. So in university, I used a lot of the R inbuilt data sets and generated many linear models. Now, does anyone recognize the plot on the screen? Yeah, it's a pretty classic plot, and I generated millions of these in uni, and it almost seemed trivial assumption checking to me, as the assumptions were always satisfied and there was literally nothing to worry about. So then fast forward a year, working at the Australian Bureau of Statistics, I had some censored data and I wanted to apply the Cox proportional hazards model. This model was fantastic and there were some data assumptions, but need not worry, it's nothing to worry about. For good practice, I checked these data assumptions and they were not satisfied. So instead of giving up, I decided to see what I could do, and I investigated a method of time domain restriction. So today I'm going to be presenting some like my proposed method, and I'll present it in context of the Cox proportional hazards model, but I would encourage you to consider applying this approach across other models with data assumptions. So what is the Cox proportional hazards model? So it's a really useful time to event model, which can help us explain the relationship between an event y of t and a set of explanatory variables x1 up to xt. So I have an example on the screen which might hit home for some of us. So y of t can be time until a statistical graduate finds work, and our explanatory variables might be level of study completed, number of internships, and where you studied. I know we are having a careers keynote talk later on, so I'm sure this model will get debunked. But long story short, this model can tell us which of these variables have an impact and their magnitude of impact. And a really great part of this model is it can account for censored data. So if we say have a statistical graduate who hasn't found work on day 60, we can still include them in the model. So it's a very useful model. So the dreaded assumptions. So in maths words, the assumption is that there is independence between residuals and time, and you test this by correlating the set of scaled Schofield residuals with time and testing for independence. Now, a little bit more simply, and what hits home for me, is that the impact of these explanatory variables is constant over time. So for example, the impact of living in the South Island of New Zealand on your job prospects is the same on day 3 and on day 60. It does not change over time. And the way you test this in R is you load the survival package in, the serve-miner package, and then you put your model through the cox.zph function. And you have to look for non-statistically significant p-values, as we want a non-statistically significant relationship between time and the explanatory variables. So you want our p-values to be greater than 0.05. And I do acknowledge this does come a little bit unnaturally as a statistician, because often we are looking for those significant p-values. So whilst I would love to show you the ABS data that violated this assumption, that just isn't possible. But instead, I will show you some results from the veterans data set, but the results were similar with the ABS data. So the veterans data set compares the impact of 2 treatment regimes and other factors such as age, prior treatment, and cell type on lung cancer prognosis. And our event Y of T is the patient's death. So I created a Cox proportional hazards model using this veterans data set, and then I checked the assumptions using cox.zph and got the following output. So we can see that cell type and Carno got a p-value of less than 0.05, so very significant. Hence, they have a significant relationship between time and these variables, and our assumption was violated, so we could not really perform this statistical analysis. So my proposed method is to restrict the time domain. So with this data set, I restricted the time domain and only looked at units who had survived at least 30 days. Now, if we think about this contextually, if we're looking at the long-term impact of treatment, if someone dies on day, say, 2 or 3, they likely died not because the treatment was ineffective, but just because it was a bit too soon in the observation window. I then noticed that there were very few units who had survived beyond 120 days. So I censored these units at 120 days. So I have an example of how I censored them. So we have the covariates, treatment type, age, and cell type. And then I inputted time as 120 and status as 0, because 0 represents that the event has not occurred at day 120. So I then remade the Cox proportional hazards model with this time domain restricted data, and the results are much better. The p-values were all greater than 0.05, satisfying these data assumptions. This is honestly very exciting that this had worked, even though it's a very small idea. And the global p-value was also greater than 0.05, meaning the model overall satisfies the data assumptions. So just reflecting on this, the key advantage is that the data is able to satisfy the assumptions, and we can statistically perform this Cox proportional hazards model. And we were able to deduce the impact of these explanatory variables. So I think I found that cell type was the most influential variable. Now, the key disadvantage is that the results are only valid between 30 and 120 days. We can't extrapolate before 30 days, and we can't extrapolate beyond 120 days. So you can get a sort of midterm, I guess, prognosis and impact of these variables. So just to finish, this method of time domain restriction has a huge potential across other time-based models with stringent data assumptions. We could apply this to time series data, regression data, or even survival analysis. And I found this technique was effective across many other data sets in R and across my ABS data. And I guess finally, this was a real challenge working this all out. And it's shown me that as a statistician, we really must be innovative when we're up against statistical challenges. And I really look forward to the rest of the conference talks where I'm sure many more innovative statistical ideas will be put forward. But thank you all for listening to my talk.
All right, thank you, Meredith. So that was the final speaker. So we have some time for questions now. So if you're in a particular hub, just raise your hand in person, but is there anyone here in the Perth hub that has a question that they would like to ask while I browse? For any of the three speakers in this particular session? Yes, Daisy.
Thanks. This question's for the first speaker, Samuel. There you go. That was a really interesting application of cluster analysis. I've never learned anything about sort of sports science statistics before. I wonder if you have any examples of when analysis such as this has actually demonstrably changed the effectiveness of teams.
It's probably a growing space, especially in that sense where coaches and the systems that are set up at the moment has been set up for a long period of time, and trying to show that this kind of analysis can assist in the analysis that they're already doing without probably the data backing at hand. So not in a negative impacting way and changing specifically. You've got the baseball examples that probably most people are aware about with Moneyball and trying to optimize a team's list with limited amount of money. So that definitely has changed performances across the world in that sense. I personally haven't experienced a negative impact on it, and hopefully not, because that's right. Hopefully will end up working as well. So I don't want to ruin it that way. But yeah, not specifically in that example, but trying to show coaches and those in that sports domain that they can optimize their time and go, here's a quick summary through some analytical methods. Ask away any more deeper questions now that you have the time, not summarizing, spending hours watching footage and that kind of things. Yeah.
So I think we have a question in the Hobart Hub.
Yep. Hi, this is Cam Patrick from Hobart. Just have a question for Meredith Norman, who just presented. So that was a really interesting talk. Thank you for that. I was just wondering, so I had always been taught that you can't restrict the time domain in survival analysis because it introduces immortal time bias. I was just wondering if that was something that you'd considered, or if I was misremembering the concerns for that. But I guess, did you do anything to demonstrate that your method didn't introduce bias in the results by restricting the time domain?
Yeah, thanks. So that's a really good question. Yes, that definitely is a limitation and something that would have to be acknowledged when you're looking at the results. That I guess you could more think about it, the collection period is only 30 days and beyond. But it would definitely introduce some bias restricting this time domain. But I guess you just have to weigh it up against with the benefit that you can get some results using this model, beyond 30 days. I guess as well, you can still generate survival curves for the entire time period, and they would be less biased. But yeah, I do get what you're saying.
Right, thank you.
Maybe time for one question. We have one here in Perth.
Hi, my question was for the most recent speaker, Meredith. So how do you decide for different data sets the restriction of your time domain? So is that something that should always have an interpretation based on the data you're collecting, or should that be informed by the actual data?
I think it's a little bit of both. So you got to like think about the context of the, I guess, the data and what you're trying to get out of it. So if you're looking at treatments and you're looking at the long-term effect, but it is like a very new idea. Like I hadn't found anything about this on the internet, so there is like no specific like pull and plug formula where you can put the data and it tells you the bounds. So it is a little bit of trial and error as well.
Right. Okay. Thanks.